Okay, before we get started, I want you to know that there's a free spreadsheet that you can try, and it's got 25 different two-stroke calculators on it, all for various things. This is engine compression, this is trapped engine volume, this is carb airspeed. It just goes on and on. There's like 25 different little calculators on it. It is all free. Download from this website right here. And all you need is, if you don't have Excel, all you need is this program right here called LibreOffice. Libre is free in Spanish. So just go to this website or just look up by Google LibreOffice and you can do the download. Choose your operating system right here and then click download. After you've downloaded this, all you got to do is open Excel or LibreOffice and click on File, click on Open, go to where the files are saved. You find that file, you double click on it, and it opens up. All the cells that are in light blue, these ones out here, are where you put the information, and the dark blue is describing what information goes there. And in this case, the squish velocity calculator, it gives you this graph over here which shows you whether it got too much, too little of each thing that it analyzes. And that's all there is to it. Keys to power. Number 1, increase the burn rate. I'm talking about the combustion. This is an Excel calculator that I made in order to prove or disprove whether or not a faster burn in the cylinder causes more rotational force at the crank. You can see at these graphs out here that as the crank degrees increase, the percentage of force that can be translated from the conrod to the crank wheel increases. It maximizes at 75 degrees. And that explains why, even though the cylinder pressure is very high in the early degrees, it starts out very low and it ramps up. So it doesn't maximize until a little bit after 15 degrees. So, and then as it goes down, that relationship becomes better, which is why this doesn't drop off at the same rate at which this is dropping off. So that's the force on the crank, the rotational force. Here we have 4 examples of combustion in the cylinder. From the blue happening very slow, peaking later, and not being fully dissipated when the exhaust port opens at 95 degrees ATDC, which is an equivalent of 170 degrees duration. Or if you wanted to cut it off right here, it would be 85 degrees, which is 190 degrees duration. So we've got these 4 examples of burn rates, from the slow blue graph to the fast orange graph. And right here is a resultant pressure inside the cylinder. You see the highest pressure is the orange graph, which is the fastest burn. And right here we have rotational force. And I added those all together, which gives me a summary saying that the gray graph gives the best overall rotational force. Second best is the red graph, and then last is a tie of the orange graph and the blue graph. You see how the orange is higher than all of them in this area right here, but it's also lower than all of them on past 35 degrees. So up to, from the blue to the red to the gray graph, yes, the faster the burn, the more power to the engine, or power to the drivetrain. And then here comes the orange graph, and it shows that you can get a little bit too much of a good thing, okay? And with this excess pressure right here, we may be looking at some detonation. You know, a lot of race teams will tune their engines to the point of detonation and then back off a bit. It all has to do with the burn time. What affects that? Squish velocity, compression, jetting, timing, and engine oil. So this calculator helped me to fully understand the subject. So now I'm very confident in saying that yes, if you increase the burn rate up to a certain limit, you're going to increase the engine power. So let's talk about different ways to increase the burn rate. Use the faster burn oil. I'm talking about engine oils, which many of the cool riders call it premix. As you know from previous videos, synthetic is the slowest burning oil. It's also highly protective, but you really don't need it unless you have a high heat engine, which is indicated by your NGK spark plug number. If you're running a number 9 or number 10, yes, you need 100% synthetic. If you're not, you're using number 8 or number 7, you do not need a 100% synthetic. If you use a semi-synthetic, it's going to make it a faster burn oil, okay, because the mineral oils burn faster than the synthetic. If you look at my oil page, you will see exactly what is in the different products. Many products say they're fully synthetic, but they're not. This is my website where you can look up the specs on most of the popular oils. Also, the fastest burn oil is castor, and if you add enough of it, like using it at 25 to 1, there'll be so much of it coating the piston top that it will insulate the piston and keep the temperatures of the piston down, and it won't burn onto the piston top like it normally does. So it's a little more expensive, but it's a speed secret. Use castor, add more of it than you normally would, increase the main jet, and retard the timing, and you will see more power guaranteed. This list shows how I categorize oils, from the full castor oils, which are fast burn, to the group 2 and semi-synthetics, which are medium burn, to the full synthetics, which are slow burn. B. Replace the piston rings if the end gap is too big. The ring end gap, or if you're going by a compression tester, you can do that. If you measure the compression after breaking in new rings, then you don't want it to be too far down from that due to the end gap becoming too big, which happens when the rings wear. Increasing compression increases power. Unfortunately, it also increases engine heat, which is why I would also recommend lathing the mating surface of the head down to increase the compression ratio. But usually engines come with a good average compression ratio that works well for the engine. C. Increase squish velocity by lathing down the head or cylinder mating surface. Almost all stock engines have less than optimal squish velocity. I don't know why this is. It has something to do with the manufacturing tolerances, but something else also. If you want more power, you increase the squish velocity because that increases the burn rate. The amount you lay off of the head or cylinder top is very minimal. It's usually just a few tenths of a millimeter, less than what you would if you wanted a sizable increase in compression. But to do this, you should know what the squish velocity is to begin with and what the recommended amount of velocity is to compare it to. And you can do that with my squish velocity calculator. D. Increase spark power with an iridium spark plug or by switching to a non-resistor spark plug or spark plug cap. It is a fact that iridium plugs require less voltage for the spark to happen. Given that the power, which is the voltage multiplied by the current or by the available current, is the same from the high voltage coil, then if you reduce the voltage requirement at the spark plug, you automatically increase the current that's happening at the spark. The more current, the hotter the spark. Another way is changing from a resistor spark plug to a non-resistor spark plug or a non-resistor spark plug cap. You should get a voltmeter that can test resistance and look and see if your cap has 5,000 ohms resistance. If you're using a NGK spark plug, the second letter will be R. That indicates the resistance inside of it, which is also 5,000 ohms. So if you're using a BR8ES, you would change to a B8ES. You would just leave out the R. I'm going to cut it short here, so I will catch you in the next video. Take care.